Okay, so we did not actually have class last week, but I did provide you with a video of the lesson, which I had taught in the Stat 2401 course. So I hope that you have reviewed that and completed quiz 4. I am going to go ahead and share the screen. Okay, so tonight's agenda, we're going to have in just a minute a very, very candid conversation about mini project number 1. And then I'm going to see if you have questions related to the normal distribution, which was the topic last week that you were asked to watch the video of. And then we're going to get into tonight's lesson, which is the central limit theorem. And then quiz 5 will be due by Sunday, September the 25th. Okay, so I have completed grading the mini project number 1s. Most of you did not do very well at all. In fact, I'm quite disappointed at the quality of the work that was submitted. We had not necessarily done all of those pieces at one time. However, we had discussed and talked about, and I alluded to the project, all of the parts on that mini project 1 multiple times in the lessons prior to its due date. You had at least 10 days to do the assignment, and I afforded you the opportunity to ask questions at least twice before it was due. A number of you don't know how to follow instructions, because when the instructions say use complete detailed sentences, I expect to see complete detailed sentences, not 1 or 2 words. A number of you did not put an appropriate title on your graphs. I know that we talked about it numerous times, that your titles should be detailed and include information like who, where, what, and when. A number of your observations of the graphs were way off base. You were either going beyond the scope of the graph or reading more into it than you should have. Almost nobody interpreted the quartiles as requested and instructed to do. I do not know if you were just in a hurry. I do not know if you failed to read the instructions. I do not know if you weren't paying attention when we were having discussions about those things in class. But I am quite honest at the quality of those submissions. I cannot believe that you would turn something like that in for a grade, much less to your employer. If that had been a task that your employer asked you to do and you turned in something as awful, for lack of a better term, I can't imagine what your employer would have to say. So I don't know what you need to do. I tried to provide individualized feedback per question on every question that was missed on the assignment. That's why it took me so long to grade it. If you have not gone back and looked at that feedback, I strongly suggest that you do so. Some of you may want to, you should be able to go back into the assignment, and once I posted the grade, published it, you should be able to see any feedback. So you should be able to go in and click on your assignment and see the feedback. I've had a request for a meeting during my office hours to talk about what the issues were. If others of you want to do that, office hours are open. You don't have to have an appointment during those times. If you wish to do it through Zoom, my office hours in Zoom are on Thursdays from 1 p.m. to 3 p.m. or on Sundays from 8 p.m. to 9 p.m. If you need something outside those windows, then you need to send an email with possible values. Let me see. I'm not going to share my screen, but let me see if I can go in and determine how you look at your feedback, because I haven't done that. I don't do that on my end. So let me see if I can figure it out, since some of you apparently are having difficulty. Give me just a minute, because I have to get into student mode. But I'm probably not going to be able to see anything because I don't have a submission. Okay, hold on just a second. I'm still checking. Just be patient. I can't do it as a student, so let me see if I can tell how to do it. It's CGHAN. Y'all use acronyms and I don't know who that is, but anyways, I will have to try to see, but the feedback is written on the rubric, so you should be able to click on the rubric and see it, but I can't do it as a student because I don't have a submission to look at. So I will, instead of wasting time now, I will see if I can figure out the keystrokes and send that information to you. But you should be able to go in and view the feedback relatively easily, but I don't know the keystrokes right off the top of my head. So give me a day and I will see if I can find those for you. All right. Any other questions or concerns before we kind of do a recap of the lesson that you viewed last week by video? Okay, the topic last week that you were asked to view by video was the end of the exponential distribution, and then I believe the normal distribution. So, and the normal distribution was the assignment quiz 4 that was due this past Sunday. So do you have questions related to that topic or to exponential distribution before we move on? Okay, I am going to share my screen, and just to ensure and feel confident that you are familiar with the material, I'm going to do a quick review of the content from the normal distribution, do a couple of examples. The normal distribution is one of the most important probability distributions that we talk about. It is a continuous probability distribution, and it is one of the most important and is probably the most commonly used in statistics. We can actually use a normal distribution to model a binomial distribution, or to model the uniform distribution, or even the exponential distribution. So it is one of the most commonly used and one of the most important. When you're looking at the problems related to the normal distribution, you should be told three things in the question. Okay, you should be told three things in the question, and I have misplaced my pen, so hold on just a second. There it is. Okay, in a question or in a scenario related to a normal distribution, somewhere in the scenario it should say that the variable is normally distributed, or is approximately normal, or follows a normal distribution. Somehow, some verbiage, it needs to imply that the distribution is normal. You should also be told in the scenario the population mean, which is represented by the Greek letter mu, and you should be told the population standard deviation, which is represented by the Greek letter sigma. You have to know those three things in order to work the problem. You have to know that it is normally distributed. You have to know the mean, and you have to know the standard deviation. Okay, so those three things are typically stated in the scenario. It is important that you carefully read the entire scenario word for word. This is not something that you can skim through. If you see it, it can be written in symbols. In symbols, we would write the variable approximates a normal distribution, in this case with a mean of 225 and a standard deviation of 10. That's kind of the shorthand notation. The variable approximates a normal, letter N, because normal starts with N, and then you're given the mean and the standard deviation separated by a comma. So in this scenario that I have, that I quickly typed up right before we started, it says the average, or the mean number of calories in a 1.5 ounce chocolate bar is 225. So it tells me that my mean or my average is 225. If I keep reading, it says, suppose that the distribution of calories is approximately normal. So there I'm told that it's normal, with a standard deviation of 10. So if I don't have to, but if I wanted to write that in symbols, I would write the variable, which is the number of calories, approximates a normal distribution with a mean of 225 and a standard deviation of 10. Then the question says, find the probability that A, randomly selected chocolate bar will have between 200 and 220 calories. Now, one thing that I want to emphasize tonight, which I think I did in the video last week, is it says find the probability that A. So A implies that we are only going to select one chocolate bar. And we want to know what's the probability that we'll have between 200 and 220 calories. So I know from the scenario that I was given that I have a normal distribution. So I'm going to draw my horizontal axis, my bell-shaped curve. I'm going to label the mean, which is the measure of center, and is given to me as 225. My points of interest are 200 and 220. So 200 would be over here on the left-hand side because 225 is the mean and is in the middle. So if you look at this as a number line, 200 would be on the left-hand side as well as 220. And I'm looking for the probability that we're between those two numbers. So I'm actually looking for this red shaded region. You have to remember, and we had this discussion when we talked about the uniform distribution, that the area under the curve equals the probability. Okay, so we're going to use Minitab to do those calculations unless you want the pleasure of doing calculus, which I'm sure most of you do not. The fact that this is a between, Minitab uses the phrase middle instead of between. So I'm going to go out to Minitab. And let me get a new worksheet. I don't really need one, but I'm going to go to Graph, Probability Distribution Plot, View Probability, click OK. It is a normal distribution. We were told that the mean was 225 and the standard deviation is 10. Then I go to options. I have a specified X value. Again, the between, they call it a middle. And we are between the values 200 and 220. I click OK. OK again. And my graph appears in the top. And I'm going to copy it over to my document so you'll be able to see it better. Okay, so this is the actual graph that comes out of Minitab. Again, you can see they have the mean labeled in the middle. They have our points of interest as 200 and 220 and the red shaded region. Your answer to the question is this number that's kind of hanging out in the space. So the probability that a chocolate bar, one chocolate bar, will have between 200 and 220 calories is 0.3083. Was that what it was? 0.3023. So my answer here would be 0.3023. So there's about a 30% chance that a randomly selected chocolate bar will have between 200 and 220 calories. Okay, considering that same scenario, chocolate bar, calories have a normal distribution with a mean of 225 and a standard deviation of 10. Let's look at this second question. It says, find the probability that a randomly selected bar will have less than 230 calories. Again, notice this one says we're doing, let me see if I can get my mouse where it needs to be, a or one chocolate bar. So again, even in this scenario, we're doing one chocolate bar, okay, because of the A. So I know that it's normal, so I'm going to draw my distribution. I have my horizontal number line, my normal bell-shaped distribution. The mean is the measure of center, which is given as 225. And we want to be less than 230. So my point of interest is 230, which would be to the right of the mean because 230 is bigger than 225. Think of it as a number line, and we want to be less than that. So I'm looking for this area or this region to the left. Less than is to the left. Okay, so this is less than. Less than, again, which is to the left. This is called a left tail. Tail is usually refers to the end, and so we go all the way out to the end of the curve, which technically never ends because it's continuous. So using that information, we go out to Mini tab, go through the steps again. Graph, probability distribution plot, view probability, click OK. We have a normal distribution with a mean of 225, standard deviation of 10. Options, this time we have less than, which is a left tail, and we're to the left of 230, which is our point of interest. I click OK, OK, and again, it creates the graph for me, which I'm going to take over to my document. So again, you can see the picture that Minitab draws. And again, what you're looking for is this value that's kind of hanging out in space that represents the red shaded region. So in this case, the answer is 0.6915. So there's about a 69.2% chance that a randomly selected chocolate bar will have less than 230 calories. And then one more. Same scenario, it says find the probability that a randomly selected chocolate bar will have more than 227 calories. Again, note that we're selecting one chocolate bar because of the A. We know that we have a normal distribution because we're told that in the initial scenario. So I have my horizontal axis, my bell-shaped curve, the mean in the middle, which is 225, and I'm interested in whether the number of calories is greater or more than 227. 227 is still going to be on the right-hand side because it's slightly bigger than 225, and we want to be more than is to the right. So that's this red shaded region here. So the fact that it is more than is always to the right. This one is called a right tail. So again, we go out to Minitab, graph, probability distribution, view probability, click OK. It is normal with a mean of 225, standard deviation of 10. This is a greater than, which is a right tail. My point of interest is 227. I click OK, OK, and again I get the graph. And I'm going to copy it again over to the document so you guys can see it. And again, what you're looking for is this value that's kind of hanging in the space that represents the red shaded region. So it's 0.4207. So there's about a 42% chance that a randomly selected chocolate bar will have more than 227 calories. Now that's a quick recap of the lesson from last week. Do you have questions?
Ms. Ralston, I have a question.
Yes.
So I remember like kind of going through the quiz and seeing all of those examples or those problems, but I feel like I remember there were 4 scenarios. So you have like the right tail, left tail, and then middle, but there was one like or, like a problem with like
Yes,
with an
ma'am.
or.
Yes, ma'am.
Can you show that to me? Because I felt like a couple of those on the quiz were one of those scenarios, but my answers weren't coming out like anywhere close to what I thought they would be. So I was kind of just trial and error and realized that that was not one of those scenarios. Can you show me an example?
I'm making one up, Jada.
Okay, thank you.
Okay, Jada's right. There actually, if you watch that video, there are really 4 different scenarios that you can have. You can have the between, you can have a left tail, you can have a right tail. The example that she is alluding to is one where you have an or statement, such as this one. And I kind of put it in the wrong place. Let me move it down so I don't get it mixed up. Okay, so it says find the probability that a randomly selected chocolate bar will have less than 217 or more than 270 or 229. Okay, so this is an or. This particular scenario is special. Okay, this is a special case because it requires you to do a manual calculation. So the or is a special case. Minitab will calculate it, but it doesn't calculate it directly. Let me see if I can show you what I mean. Okay, so we know, again, notice we're selecting a chocolate bar. So again, it's 1 chocolate bar. And we know that we have a normal distribution. So I have my horizontal number line, my bell-shaped curve, my mean is still in the middle, which is given as 225. In this case, I have 2 different regions because it says less than 217. So I've got 217 and I want to be less, or I am more than 229. So you really have two shaded regions. And honestly, I guess there's two ways you could do it in Minitab. I demonstrated what I guess I view as the easiest. Now, if you look at your options in Minitab, there are 4 of them. Right tail, which is greater than, left tail, which is less than, middle, which is the between. The other one that Minitab has is equal tails. It's assuming that you are the same distance below and above the mean. Well, I don't know that for the problem that I just made up off the top of my head. In fact, it's probably not. So I can't use equal tails. You are probably never, ever going to use equal tails, at least in this course. So we have to have an alternative way to solve this problem. What I am able to do is think about it like a pizza. I can use Minitab to figure the middle that's between 217 and 229. And I'm going to remove the middle of my pizza. So I have one whole pizza, and we use 1 because remember we talked about it, that the area under this curve is 1 because the maximum probability is 1 or 100%. So I take 1 and subtract the middle. And if I take out that middle, what's left are those tails. You will not use equal tails at all in this class. Okay, this is the easiest way to do it, is to calculate the middle, but then you have to take it one step further and do 1 minus the middle. That's why it's a special case. You cannot just read it directly from Minitab. So I'm going out to Minitab. Walk through the steps again. Graph, probability distribution plot, view probability. It is a normal distribution with a mean of 225, standard deviation of 10. I'm going to options. I do have a specified X value. I'm going to use the middle, and I'm between 217 and 229. Now, when you look at this graph, in just a minute when I get it up here, okay, notice, let me see if I can make it smaller where we can get it up there together. Okay. Notice that on the graph that Minitab created, I have this center part colored, not the tails. Again, because we did the middle. So it tells me that that middle is 0.4436. So I've calculated, get a different color, that this middle, the area here in the middle is 0.4436. But I don't want what's in the middle. I'm going to take it out. So I'm going to do 1 whole minus 0.4436. And then I'm going to do that subtraction on my calculator. So I do 1 minus 0.4436, which gives me 0.5564. That would be the answer that you want to enter if you were doing this problem on a quiz. Even if you're doing it on a quiz, you got to remember the basics of probability. All probabilities are between 0 and 1. So you can't have a negative value, and you're never going to have a value over 1. So if you got an answer that was bigger than 1, hopefully that was a big clue. Whoops, I've made a mistake. But this is a special case. You don't see this one very often. You're going to more often see left tail, right tail, or the between. Is that good, Jada? Jada?
Yes, I'm sorry. I was trying to move my mouse. Yeah, I thought that what I was doing was wrong. But I think I just got tripped up on the wording of the problem.
Okay.
Thank you.
You're welcome. Other questions? Now, a lot of what we're going to do tonight is going to look very much like what we just did, with a twist. We're going to talk about one of the most important and useful tools or useful rules in statistics, and it's called the central limit theorem. And so I posted in D2L sometime this morning an updated version of the PowerPoint, okay, and it's labeled central limit theorem. We don't really talk about central limit theorem in statistics 1401. And honestly, sometimes it's kind of goes on behind the scenes. Okay, but it's an important rule or an important tool in statistics that you really need to understand what is going on. And this is going to get a little bit into some of the theory, some of the underlying foundation that we don't normally talk about. But I want you to try to understand how useful this theorem is and how it works, or in some ways why it works. I don't necessarily know why it works, but I know how it works. Okay, so the central limit theorem, again, is one of the most powerful and useful tools in all of statistics. Knowing that your data is going to behave in a certain way, even if it's not normal, is a powerful tool. We often abbreviate central limit theorem so that we don't have to literally write central limit theorem out as CLT. In good old everyday layman's terms that hopefully you can understand, ultimately what the central limit theorem says and or does is it forces any distribution, whether it's an unknown distribution, a uniform distribution, an exponential distribution, a binomial distribution, an exponential distribution, regardless of what distribution it is to start with, the central limit theorem, when applied correctly to the distribution, forces that distribution to be normal if a large enough sample is selected. Now there is that predicate there, if a large enough sample is selected. So we have to think about, and we'll talk about in a minute, what that means. What does it mean to have a large enough sample? There are two versions, or your text calls it alternative forms, of the central limit theorem. One is related to or uses the mean. The other uses the sum. And we are going to address both of them. We're going to start with the central limit theorem for the mean, or if you want to think about it, version 1. Okay, so here's what it says, kind of with some of the math lingo language in there, but hold on. It says, if we collect samples of size n with a, quote, large enough n from an unknown distribution and calculate each sample's mean and create a histogram of those means, then the resulting histogram will tend to have an approximate normal bell shape. It's basically saying in all that lingo, what I just told you, that the central limit theorem will force any unknown distribution to become normal if I choose a sample with a large enough n. Well, how do we know when we have a large enough n? Well, first of all, if you go back, and you may not recall this, and that you may not have been told this in your previous stats course, but the magic number in statistics is 30. At 30, what's called the student's t distribution begins to mimic or model the normal distribution. And that's probably typically true for most of your distributions, even with, say, the binomial distribution. When your sample size is 30, it begins to mimic the normal distribution. So if you know that a distribution is normally distributed from the beginning, then a sample of 30 would be adequate, and you possibly could have less than 30 because you know that it's normal. But if you don't know, see, this says if you have an unknown distribution. So if I have an unknown distribution, then I pretty much have to have 30 or more. So n has to be at least 30 or more if we have some unknown or not normal distribution. Okay, but it ultimately comes down to your original population, because you got to think about what type distribution is that original population. Do you know that it's normally distributed, or do you not know what it is at all? Or do you know that it's, say, uniform or binomial or some other distribution? Again, if the original distribution is like way, way off from being normal, then you may want to have a lot more than 30. But 30 is kind of our magic number. Okay. And really, anytime in statistics, the more data or the more items you have in your sample, the better it's going to be. More data is always best. The result of the central limit theorem for the mean is, again, if we take each sample and calculate its individual mean, and then we create a histogram of those means, the resulting histogram is normal. So I then have a normal distribution, and I need to know the mean and the standard deviation of that normal distribution. That's how all normal distributions are defined. They're defined by their mean and their standard deviation. So those two parameters become the mean of the central limit distribution is equal to the mean of the original distribution. And I'm going to show you this in just a minute. And the standard deviation of the central limit theorem is equal to the ratio of the original standard deviation divided by the square root of the sample size. And I'm gonna show this to you in just a minute. So I want to try to prove this to you or show you how this works. using an example that I created years and years ago. So we're going to take a look at or think about Social Security numbers for a minute. You may not know and you may not care, but your Social Security number is a 9-digit number that you are assigned by the government. Typically, it has 3 digits in the beginning. It's divided up 3 digits, 2 digits, 4 digits. The first 3 digits is called the area number, which are assigned to a particular geographical region. So the government could look at those first 3 numbers and kind of get an idea of the region of the country where you were born. The second set of 2 digits is called the group number. And that's a number that's assigned to a particular area within a state, and it has a rotation of odds and evens. So, one year it might be odds, the next year it might be evens. The last 4 digits of your Social Security number are called the serial number, and they are supposedly assigned at random. So, gosh, probably 10, 15 years ago, I had access to students' Social Security numbers because they were used as your ID number as opposed to the 9,000 numbers that we now use. When identity theft and all that kind of became rampant, a lot of places moved to using some randomized number. So we created the 9,000 ID number or 9,001 ID number. But so the last 4 digits, I collected the last 4 digits of the Social Security numbers for the 131 students that I had during that particular time. So I have 4 numbers from 131 people. Well, I don't know what kind of distribution that is, so I have an unknown distribution. I created a spreadsheet. I took an Excel and I entered those 4 digits. So I have for 131 rows where I have the 4 digits, and each digit is in its own column. Okay, so like 0, 1, 7, 6 would be the last 4 digits of that individual's number. So then I took each one of those columns and I created a histogram. And let me get back to the PowerPoint. Okay, and when I do that, look at this histogram. This is the histogram of the last 4 digits of the Social Security numbers for those 131 people. So I had a total of 524 numbers. And they're color coded because column 1 was blue, column 2 was pink, and so forth. But look at this distribution. What shape does that look like? Does it look normal? I certainly hope that you don't think it looks normal. If you look at it, it almost follows, and mine's a little crooked, a uniform distribution. Now again, it's not perfect, but no distribution is. So if you look at the individual data values, I had 131 people, 4 digits for each person. That's 524 digits. If I look at those 524 individual digits, my distribution appears to look uniform, which ain't normal. If I calculate the mean of those 524 numbers, we get 4.45229, and the standard deviation is 2.897156 for those 524 numbers. I then took using the central limit theorem for the mean, it says take the mean of these numbers. So to find the mean, I added the numbers up. 0 plus 1 is 1, plus 7 is 8, plus 6 is 14, and 14 divided by 4 is 3.5. Then I did the second row. 5 plus 0 plus 4 plus 0 is 9. 9 divided by 4 is 225. So I have 131 means for each set of 4 digits. If we look at the histogram of those means, which is what the theorem says, calculate the sample mean and then create a histogram. When I create the histogram, the original distribution was uniform. The distribution of the mean is normal. Now again, it's not a perfect normal distribution, but guys, it's pretty darn close. You get that bell shape. Okay, so again, I just proved to you through real live numbers that the central limit theorem works. If we select a sample size of n, which in this case we had 4, if we select enough samples of 4 and look at the means, I can force a uniform distribution, in this case, to become normal. If I then take the mean of those means, I get 4.45229, and the sample standard deviation for the central limit theorem is 1.4. If I take the standard deviation of the means, I get 1.475803, and we had 131 groups of 4. So check this out, guys. This is our original distribution, and this is our central limit distribution. And the two results, the two things that come out of this that are important to you are that the mean of the original is equal to the mean of the central limit theorem. And if you look at these numbers, guys, look, 4.5229, 4.5229. I didn't make it up. Those are the actual numbers when you run the statistics. Now notice the difference in the notation. We have to have a way to distinguish whether we're dealing with the mean of some unknown distribution or the mean where we have applied the central limit theorem. To show that we are using the central limit theorem, you'll see it written with a little subscript of X bar. Remember, X bar is the symbol for the mean. So we're looking at the central limit theorem for the mean or the means. And so you see that little subscript there to indicate that we have applied the central limit theorem. So just a slight adjustment in the notation, but the mean of the original is equal to the mean of the central limit theorem. Similarly, for the standard deviation, it tells us that the standard deviation of the central limit theorem, again, you have that subscript of X bar to indicate that that is the central limit theorem that we're using, is equal to the original standard deviation divided by the square root of the sample size. So in this case, that means I would have the original standard deviation, which is 2.897156, divided by the square root of 4, because we had 4 digits, so my sample size was 4. So I have 2.897156 divided by 2. And if I do that math, divided by 2 is 1.448578. So that would equal the standard deviation of the central limit theorem. Now, if you notice, the number that we got over here is a little bit off from that. But guys, I'm still in the ballpark. So the central limit theorem works. I've just proven it to you. So you may say, well, Miss Ralston, big deal, whoop-de-doo, what does this mean to me? Okay, so let's look at, and it's on this next slide is the question, but I've put it over onto my paper so we can make notes on it. Okay, so here's an example of where we might apply the central limit theorem, and I want you to notice the difference in the way the question is written. Okay, it says, the length of time taken on the SAT for a group of students has an unknown distribution with a mean of 3.5 hours and a standard deviation of 1.2 hours. A sample size of n equals 100 is drawn randomly from the population. Okay, so if you go back to the problems that I worked initially, I told you that it had to say normally distributed, it had to give you the mean, and it had to give you the standard deviation. You get some of those things in this problem. The one thing that jumps out at me that I don't know is I don't know that it's normally distributed. It clearly says I have an unknown distribution, but it does give me the mean. It does give me the standard deviation. It also tells me that I'm going to draw groups of 100 as opposed to A. Remember, I kept pointing out to you that A chocolate bar meant we had 1 chocolate bar. Well, here, instead of drawing 1 chocolate bar, we're going to draw 100 chocolate bars. And then we may go back and draw 100 chocolate bars a second time, and a third time, and a fourth time. Okay, so we're dealing with groups. So my biggest clue here that I want to use the central limit theorem is that I'm going to be using groups as opposed to a single. So I know that I need to apply the central limit theorem because I'm going to select groups of 100 in this particular case. So because I need to apply the central limit theorem, one thing that I know is going to be that because of the central limit theorem, my unknown distribution is going to become normal. Okay, so I'm going to, by applying the central limit theorem, I'm going to force that unknown distribution to become normal. But I need to determine what the mean and the standard deviation of that normal distribution is going to be based on the formulas that we just looked at a minute ago. Okay, so for the mean, we're told that the mean for the central limit theorem is equal to the mean of the original. The original is given to me as 3.5. So quite honestly, the answer to this question is given in the scenario. Then we need to determine the standard deviation. You need to read carefully because it says, what is the standard deviation you will use for this problem when looking at the average? That word is important. Of the 100 people and round to 3 decimal places. I know because the way this question is worded, we've already decided that we're going to apply the central limit theorem. But in this case, the way this is worded with this word average, that lets me know that I'm going to use the central limit theorem for the mean. And again, that helps me to determine the formula or formulas that I may need. Okay, so the standard deviation of the central limit theorem is the original standard deviation divided by the square root of n. The original standard deviation is given as 1.25, and it says we're going to use sample sizes of 100. It says it in the original scenario. It also says it again here in this problem. So that gives me 1.25 divided by 10, which is 0.125. And it says in the instructions, and guys, the instructions here are very important because if it says round to 3 decimal places, you will need to enter the 3 decimal places into Minitab when you go to do the calculations. If you only enter 1 decimal place, you're going to get the wrong answer, and D2L will count it wrong because the instructions clearly say round to 3 decimal places. You cannot skim these questions. You need to read them word for word very carefully and very slowly and multiple times if necessary. If you do not round appropriately as instructed, you will get the wrong answer. Okay, so I now know that I have a normal distribution with a mean of 3.5 and a standard deviation of 0.125. And I'm going to use that information to solve some problems. And I'm going to write this up here where we'll have it kind of as a notation. My variable is approximately normal with a mean of 3.5, and we often say an adjusted standard deviation of 0.125. Okay, so this says find the probability that the sample mean is between 3.25 hours and 3.75 hours. Now notice this one says probability that the sample mean. That is another difference from the way the questions were worded previously. It just says find the probability that. Okay, in this case, we're thinking about it in relationship to the sample mean, and it states that. So that's another clue. Oh, I need to use the central limit theorem for the mean. So if I draw a visual here, just like I was doing before, I have, because of the central limit theorem, I have a normal bell-shaped distribution with a mean of 3.5, and I want to know what's the probability that the sample mean is between 3.25 and 3.75. So again, I'm looking for this area under the curve. We already talked about it tonight, that the area under the curve corresponds to the probability. This is a between. The term used in Minitab is middle. So I'm going out to Minitab and I'm going to use the same commands we were using earlier. I just enter the adjusted or the central limit theorem values for the mean and the standard deviation. So we go graph, probability distribution plot, view probability. I click OK. We know that it's normal. The mean is 3.5. The standard deviation is 0.125. Entering the 3 decimal places that I was asked to round to. Options, we're doing between, which is the middle. And we're doing between 3.25 and 3.75. I click OK, OK, and it creates the graph. And again, I'm going to move it over here where you guys can see it. Okay, so you have your normal distribution. It even tells you it's normal, mean of 3.5, standard deviation of 0.125. And again, you're looking for this number that's kind of hanging out in space. So 0.9545. Okay, so my answer here is 0.9545, which means 95% of the students take between 3.25 and 3.75 hours to take the SAT on average. Okay, that little caveat there, on average, is because we did the sample mean. Now, I don't think I've looked at the quiz, and I don't think you have to go that far and offer that explanation, but you need to know how to take it to that explanation in case you ever had to explain it to somebody. All right, let's look at another one. Find the probability that the sample mean is less than 3.6 hours. So we still know that the time that a student takes to take the SAT, we have forced it to be normal using the central limit theorem with a mean of 3.5 and a standard deviation of 0.125. Okay, so I still have that same scenario. Again, it uses that phrase sample mean, which again is an extra clue that I'm using the central limit theorem. So I have my horizontal axis, a bell-shaped curve. The mean is 3.5, and it says less than 3.6 hours. So here's 3.6, and we want to be less . Okay, less than. Values that are less are always to the left. So less than is a left tail. So I'm going out to Minitab. Graph. Probability distribution plot. View probability. Okay. It's normal with a mean of 3.5, standard deviation of 0.125. Going to options, it was a less than or left tail, and we wanted to be less than, was it 2.6, 3.6? 3.6. 3.6. We get our distribution plot. And again, we're looking for this region or this value that's kind of hanging out in space. So it's 0.7881. So there's about almost a 79% chance that a student who takes the SAT will take longer, or excuse me, take less than 3.6 hours. About a 79% chance that a student who takes the SAT will take less than 3.6 hours. Okay, one more and then we're going to move on. Again, I've tried to kind of give you an example of each type that you might encounter. Notice you've had a between and you've had a less than.
Ms.
The third, ma'am.
I'm sorry. So for that one, would you not include on average as
yes,
well?
ma'am. I'm sorry,
okay.
I just forgot to say on average.
I just want to be sure.
Yes, ma'am.
Thank you.
Thank you, Jada. Okay, so find the probability that the sample mean is greater than 3.15 hours. So again, we still know, applying the central limit theorem, that my variable is normally distributed with a mean of 3.5 and a standard deviation of 0.125. So I have a normal distribution. Mean is in the middle, which is 3.5. And we want to be less than, or excuse me, greater than 3.15 hours. So 3.15, and we want to be greater. Okay, remember greater than is to the right. So we're looking for this red shaded region right here. Okay, so because this is greater than is always to the right. So that means we have a right tail. Out to Minitab. Graph. Probability distribution plot. View probability. Click OK. It's normal. Mean of 3.5. Standard deviation of 0.125. Options. We're doing right tail. 3.15. Whoops, make sure you type it right. Click OK. OK. Again, you get your plot. Now, it does look like this whole thing is shaded, but you have to be careful because there is this little bitty space way over here on the left side where it's not colored in. But my answer is 0.9974. So on average, 99.7 of students taking the SAT take more or greater than 3.15 hours. On average, 99.7% of students taking the SAT take longer than or more than 3.15 hours. Lily, you have a question? Lily? Lily, I saw
Yeah.
your hand raised. Do you have a
Yeah.
question?
I've been trying to work this with you on Minitab, and I'm not getting it to come up. It keeps saying error when I'm trying to work this the way you're working.
Okay, my first thought may be, are you using the web version or the web app version?
I'm going through it with you. I'm opening it up and went through the GHC one.
Okay. So how far are you getting? Does it do graph? Would let you choose graph?
It does, and I can get down to the probability distribution plot. And I select the view probability.
And click OK.
I do. And I can get all these numbers in and go through options. And when I click the tab and put the tail this under the specific X and the
Okay,
3.1.
Do you have the blue dot next to a specified X value?
I do.
Okay.
And when I click X tail or left tail or right tail, it says it's not available or the value is incorrect.
Okay. Can you stay when we're finished and I'll let you share your screen so I can see it and we'll try to figure it out, okay? Do you mind staying for a few minutes when we're done?
I will, thank you.
Okay. All right. So that gives you an example of the central limit theorem for the mean. I've tried to point out to you the phrasing that you're going to look for, and then it's pretty much the same process that you were using last week for normal distribution. Are there other questions before we look at the central limit theorem for the sums? Okay, I'm going back to the PowerPoint then. And we need to look at the second version of the central limit theorem. The second version of the central limit theorem relates to the sum of the sample instead of the means. It basically says the same thing. It says if we collect samples of size n with a large enough n from an unknown distribution and calculate each sample's sum instead of the mean. And the word sum, if you don't remember, means to add. And then create a histogram of those sums. The resulting histogram will tend to have an approximate normal bell shape. And again, we have that discussion of, well, what does it mean to be large enough? It's the same guidelines as we had before. If you know that it is normally distributed, okay, you could have 30 or maybe less if you know that it's normally distributed. But if you don't know that it's normally distributed, you have some kind of unknown distribution or a distribution that is not normal, then you have to have a minimum of 30 and more is better. It's the same guidelines. If you'll notice this funky looking notation over here, This is the symbol for sum. In mathematics, this big funky looking E thing is the Greek letter sigma. And anytime you see that in algebra, pre-calculus, calculus, statistics, it means to add or total the values. So this is telling me to add all the X values. So that's the symbol. Again, what's happening is it's going to take that unknown distribution and force it to become normal. And for the normal distribution, we need two parameters. We need the mean and the standard deviation. And the formulas change slightly. The mean for the central limit theorem sum is equal to the sample size times the original mean. And the standard deviation is of the central limit theorem sum is the original standard deviation times the square root of the sample size. Okay, so you have different formulas here for calculating the mean and the standard deviation. But again, let me try to prove it to you so you can hopefully see that this does actually work. So if we go back to our Social Security example, we've already said that if we look at the 131 people, we have 4 digits each. So that's 524 individual digits that visually this graph had a uniform distribution. And that the mean was 4.45229 and the standard deviation was 2.897156. We had a sample size of 524. What the central limit theorem for the sum says is you're going to take those 4 digits and you're going to add them together. So if I do 0 plus 1 plus 7 plus 6, I get a total of 14. 5 plus 0 plus 4 plus 0 is 9. 1 plus 2 plus 7 plus 4 is 14. So I added the 4 digits, the last 4 digits of each individual's Social Security numbers, and I added them together. I then created a histogram of those sums. When I create the histogram of sums, again, notice that I basically get a very nice bell-shaped distribution. Now this one looks a little wonky when you start looking at the numbers because it says the mean of the sum is 17.809. The standard deviation of the sum is 5.903. And we did have 131 groups of 4. Let's put those numbers side by side again. You've seen it visually. What it tells us is that the mean of the central limit theorem by the sums, and you may see it with that little funky E symbol down there, okay, or they'll write it out in words, mean of X sum is equal to the sample size times the original mean. So for this problem, just to kind of let you see the numbers for this problem, that means I would have my sample size was 4 because I had 4 digits for each person. The original mean was 4.45229. If I multiply those together using my calculator, I have 4 times 4.45229, which comes out to be 17.80916, which is the mean of the sum. For the standard deviation of the sum is the original standard deviation times the square root of n equals the standard deviation for the sum. So in this case, we would have 2.897156 times the square root of 4, which is 2. So 2.897156 times 2 is 5.794312. So I'm a little bit off from what I got when I actually used the true numbers. But again, I'm in the ballpark. So the central limit theorem works, whether you're using the means or whether you're using the sums. I will tell you that from my experience, you'll see the central limit theorem for the mean used more often than the central limit theorem for the sums. I quite honestly don't remember learning the second version, the central limit theorem for the sum. I probably did, but I don't recall it. So it's not something that we must have used a great deal. So let's look at some of these examples, or look at this example. So again, notice how this is worded. It says an unknown distribution has a mean of 90 and a standard deviation of 15. A sample size of size 80 is drawn randomly from the population. So again, it tells me that I'm going to draw a sample of size 80. So again, I realize that I'm going to be dealing with a group as opposed to an individual, which again lets me know that I need to apply the central limit theorem. When I apply that central limit theorem, the unknown distribution that I have is going to become normal. And I need to determine the mean for that normal distribution and the standard deviation for that normal distribution. And the way the question is worded, like on your homeworks and on your quizzes, and on the midterm, it says, what is the mean of sigma x? And remember, I just told you, and let me write it for you, never mind, that this notation means sum. So the mean of sum, what is the mean of sum? But then it also emphasizes you want to use the central limit theorem for sums formula. So the formula is the mean for the sum is the sample size times the original mean. So my sample size is 80. My original mean is 90. So the mean of sum is 7,200. Then it asks you, what is the standard deviation of sum? And again, it emphasizes to use that formula. For standard deviation of sum, it is the original standard deviation times the square root of n. So I have the original standard deviation, I don't remember, was 15. And n, or the sample size, was 80. Now this is likely going to lead to a decimal. It doesn't indicate here, but it should indicate in the question how many decimal places to round to. So 15 times the square root of 80 is 134.16. And let's say it said round to the nearest whole number. So to the nearest whole number, this would be 134. Again, follow the instructions and round as indicated, or you will get the wrong answer. So then we go on. So we now know we have a normal distribution with a mean of 7,200 and a standard deviation of 134. So the question says, find the probability of the sum. Notice that in this problem, it uses the word sum. So again, that is my clue, or one of the clues, that I'm using central limit theorem for the sum. So I'm going to sketch me a picture. I know that I have a normal distribution. The mean of sum is 7,200. I'm interested in whether or not, or the probability that it is more than 7,500. More than or greater than would be to the right. So because this is more than, this is a right tail. It's the same process, guys. Don't overthink it. Kind of the new piece here is finding the appropriate mean and the appropriate standard deviation based on which version of the central limit theorem you need to use. So I'm going to Minitab. Graph, probability distribution plot, view probability. It is normal. My mean is 7,200. The standard deviation is 134. Oops, 134. We were, what was it? Right tail, so more than 7,500. So right tail, 7,500. Click OK. OK. And there's our graph. Now again, you may have a hard time seeing it, but it is out here on the end. Okay. A little bit of shaded red region right here is 0.01258. 0.01258. So the probability that the sum of the values is more than 7,500 is about 1.2 or 1.3%. We don't use the word on average here because you're using the central limit theorem of the sum. So we're saying the sum is more than. Okay, same scenario. We know that we have a normal distribution with a mean of 7,200 and a standard deviation of 104 when we apply the central limit theorem for the sum. It says, find the probability that the sum of the 80 values is less than 7,000. So again, if we draw us a picture, we have our normal bell-shaped distribution. The mean is in the middle, which is 7,200. We want to be less than 7,000. Okay, so there's less than 7,000. Since it's less than, less is always to the left, so it is a left tail. To mini tab we go. Graph, probability distribution plot, view probability, click OK. It is normal. Mean is 7,200. Standard deviation is 134. Options. It is a left tail, and we want to be less than 7,000. Click OK. OK. Get the graph. There it is. So we get, again, the number is there. It's hanging out in space. It's 0.06778. Okay, so my answer here is 0.06778. So the sum, the probability that the sum is less than 7,000 is about 6.8%. Okay, one more. It says find the probability, we have the same distribution, find the probability that the sum of the 80 values is between 7,100 and 7,600. So we have, again, we know we have a normal distribution by applying the central limit theorem for sum. The mean of sums is 7,200. We're interested in the probability that we're between 7,100 and 7,600. Okay, it is a between. The term used in mini tab is the middle. Graph, probability distribution plot, view probability. It's normal, mean is 7,200, standard deviation is 134. Options, we're in the middle. We want to be between 7,100 and 7,600. We click OK, OK, and we get the graph. So we have 0.7708. So the probability that the sum is between 7,100 and 7,600 is about 77%. Okay, so again, we're really just extending what we know about the central limit theorem, or excuse me, about the normal distribution. We're applying the central limit theorem to force an unknown distribution to be normal. So then I can work the problem as if it were a normal. several things I would caution you about. You have to know, you're going to have to be able to distinguish, when do you use just straight out normal distribution? When do you use the central limit theorem for the mean? And when do you use the central limit theorem for the sum? I've got 3 examples there, and I'll come back to them in just a minute. But guys, you are going to have to pay attention. I cannot stress that enough. The details are important. The words are important. You're going to have to slow down, read the scenario word for word, and pay attention. If you're being asked to find the probability of an individual value, those were the first 3 top problems we did, or 4, as a review from last week. We did not use the central limit theorem because in each of those problems about the chocolate bars, we were only selecting 1 chocolate bar. That is a straight out normal distribution. And it should somewhere in the scenario tell you that it's normal and give you the mean and give you the standard deviation. If you're dealing with the last 2, and I don't have a note there, but I'll kind of make a note here to the side. The last 2, one of the clues that you're going to apply the central limit theorem is that instead of selecting 1 item, you're going to select a group of items. Okay, so that's one clue that you're doing central limit theorem. Then you have to decide, are you doing the mean or the sum? And usually it's going to say somewhere in the problem, it's going to talk about the sample mean or the sample average, or we'll say the sum. Okay, so you have to look for those words. So we come back over here. I have the same question with different phrasing. Okay, so the first one says the average teacher salary in North Dakota is $29,863. Assume a normal distribution with a standard deviation of 5,100. What is the probability that A, randomly selected teacher's salary, is greater than 40,000? Notice in this problem, they tell you that it's normal. They tell you the mean or the average. They tell you the standard deviation, and we're doing A, or 1 selected teacher. That is phrased in such a way that I'm just going to do a normal outright. I do not apply the central limit theorem because I've only selected 1. The second one is worded very similarly. It does actually tell you it's a normal distribution, which is okay. It again gives you the mean. It gives you the standard deviation. But then look at the question. It says, what is the probability that the mean for a sample of 80 teachers? Okay, so immediately I see I've got a group as opposed to 1, and it says mean. So that lets me know I want to apply the central limit theorem and specifically the version related to the mean. The last one, again, they do tell me it's normal, which they don't have to do if we're doing central limit theorem, but it can still be normal. It again gives me the average. It gives me the standard deviation. And it says, what is the probability that the sum in a sample of 80 teachers' salaries? Okay, so again, we have a group. So the group is one clue that I want to do central limit theorem, and then it talks about sum. So I'm going to use central limit theorem for the sum. you're going to have to pay attention. I cannot stress that enough. And be careful. Pay attention to how you're asked to round. Because if you enter it incorrectly into Minitab, even if you're only 1 decimal place off, it will likely give you the wrong answer. Okay, so that's central limit theorem. Do you have questions?
I think I figured out what I was doing wrong. I had a number in the wrong place.
Okay. Okay. I'm glad you figured it out. Other questions? Okay. Quiz number 5, which deals with the central limit theorem, is due by Sunday, which is September the 25th. Next week, we will talk about confidence intervals and sample size estimation. Okay, confidence intervals is something that we do talk about in statistics 1401 if you've had it recently. If it's been a while, you may not have covered that topic, so it might be new for some of you. I will also tell you that mini project number 2 is related to that topic. You have to create some confidence intervals. And so we're getting ready after next week to do the second mini project. Again, if you have questions related to mini project 1 and you want to talk with me, we can do that by phone. If you want to do it through Zoom, I have Zoom office hours on Thursdays from 1 o'clock to 3 o'clock. You do not have to have an appointment. You can pop in. Or I have them on Sunday from 8 p.m. to 9 a.m. or 9 p.m. excuse me, 8 p.m. to 9 p.m. Okay, outside of that, if you need a time beyond those and you want to meet through Zoom, you can send an email with several options for days and times, and I will try to accommodate you to the best of my ability. Other questions? Any concerns? Okay, if not, I will see you guys next Tuesday night. So have a good evening.
Thank you. You too.
Thank you.